Hello! In this video, we are going to prove the following theorem. Let a and r be real numbers where r is not equal to 1. Then, the sum from I equals 1 to n of a r to the I minus 1 is equal to a times 1 minus r to the n over 1 minus r for all positive integers n. So really, this is often referred to as the geometric series formula, and we're going to prove it. And the approach we're going to take is we're going to use mathematical induction. So let's start with the base case, right? In the base case, we're going to prove that this is true in the case where n is equal to 1. And what that means is that we're going to prove that the sum from I equals 1 to 1 of a r to the I minus 1 is equal to a times 1 minus r to the 1 all over 1 minus r. So let's start by writing the left-hand side. Now, since the lower and upper bounds of our sum are equal, it follows that this entire sum is just equal to ar to the 1 minus 1. So really we have ar to the power of 0, and we know that anything to the power of 0 is 1, so really we have a times 1, which is just a. But then a is equal to a times 1 minus r to the 1 all over 1 minus r. Right? Because the 1 minus r and the 1 minus r cancel out. So as you can see, we've proven that this is equal to this, which means that we've proven that this is true in the case where n is equal to 1. So this completes the base case. Now let's move on to the induction step. Now in the induction step, we give ourselves an arbitrary positive integer n, where this is true. And our whole goal now is to prove that this is also true for n plus 1. So what that means is we're trying to prove that the sum from I equals 1 to n plus 1 of ar to the I minus 1 is equal to a times 1 minus r to the n plus 1 all over 1 minus r. So let's start by writing the left-hand side. Now, because the upper bound is strictly bigger than the lower bound, what we can do is we can pull away the n plus 1th term of this sum and rewrite this as the sum from I equals 1 to n of ar to the I minus 1 plus ar to the n plus 1 minus 1. Right, so we can all agree that these two things are equal. And of course, in the second term, the exponent simplifies to just n. Okay, now, by our induction hypothesis, we know that this sum is just equal to this. And we can combine these two terms into a single fraction by getting a common denominator of 1 minus r. So combining these two into a single fraction, we get, and if we distribute across these parentheses in the numerator, what we get is, we see that the negative ar to the n plus ar to the n cancel out, so in the numerator we're just left with a minus ar to the n plus 1. And then factoring out an a in the numerator, we are left with this. So really, this is equal to this. So what we've shown here is that this is also true if instead of n, we have n plus 1, which is exactly what we wanted to prove. So this completes the induction step. And so we've completed all parts of the induction, which means we have proven for all positive integers n that this is true. So this completes the proof. And so yeah, this is one way in which you could prove this formula. And yeah, that's pretty much it for this video.